Hello, Stefan. How are you doing?
I'm doing great here. Hi, VJ. Yeah, finally back from the Haldon Festival, the Haldon Pop Festival, and there was the one where we did the tracking with a 48 channel Metric Halo setup.
Oh, yeah. Why don't you tell
Uh,
me a little bit about that?
yeah, and yeah, it was great. Absolutely fantastic. 3 days with great bands, fantastic music, and incredible. It was kind of stressy, but yeah, but awesome at the same time. This is incredible when you see so many good bands out there and with great music. At least it was 26 bands, and we tracked nearly like something 570 gigabyte of audio files.
Wow.
Yeah, and it was amazing how they organized anything because they got so different kind of music there on the stage, and they have something like 15 minutes to make all the changes in the setups there with the microphones and anything, and yeah, great, was great,
So
and
now the rig was you said 48 channels, so you had six
mm,
units, right?
yeah,
Were
it
they
was
all Leo ULN8s, or how was it
yeah.
configured?
Yeah, it was 5 ULN8, and then we have a 282. It's just running the atmospheres, the Atmo microphones,
Okay.
and then we have also some line inputs, and yeah, and we have there was a three channel microphone splitter directly on the stage,
Okay.
and then we have our own channels on split from the microphone splitter, and so we can adjust our own gains, which was very very important.
So through the recording, you had all of the channels were coming in through the split, and they
Hmm.
were going to front of house, to monitors, and to you.
Yeah, right, and exactly, yeah.
And so then to you, you were getting microphone level signals, and you were setting the levels for the preamps for the ULN8, and then
Hmm.
running directly into the Mio, from the Mio into what, the record panel?
Yeah, we did it in record panel, and we use Logic for monitoring. So we made a big aggregated device so that we have just one sum point to get a summing point where you can listen to the things, which makes it a bit easy. But finally, on the second day, we're just running with the record panel because this was very nice. They grouped everything into 8 channels. We had the drums on 8 channels, the guitar, bass, and synthesizers, percussion, strings, and stuff. Everything was in 8 groups and in a group of 8 channels, and that what makes things pretty easy. So we just take your headphone, go from one box to the other, and adjust the leveling. Just this is in this case like that. You're just sitting right 20 meters away from the stage. It's just for is the microphone there or is it not?
Right.
And that's enough. That's very pretty sufficient for that.
Okay, but on the
Yeah.
first day, you had Logic running, and you had a mix running in Logic across all
Hmm.
six boxes that was fed
Hmm.
back out to one of the boxes for headphone monitoring, for so you could solo things and that sort of thing.
Yeah. Right.
And
Right.
that went smoothly.
Well, we had some problems at the end of the day, and then we decided to go on without Logic.
Okay.
Yeah.
Um,
Good.
so you had 48 channels. What sample rate
Hmm.
were you recording at?
48K.
48 channels, 48K. So you were
Hmm.
using two FireWire buses.
Yeah, right.
And
Exactly that way.
what computer were you recording onto?
Oh, this was a 4 years old Mac Pro.
Okay. And
Yeah.
so did you had a FireWire card in the PCI
Hmm.
base slot?
Yeah, exactly. Yeah, that was really giving us two FireWire ports, two individual FireWire
Buses.
ports. Yeah, two buses. Yeah,
Right.
yeah,
And
yeah. That was pretty awesome.
so a 4-year-old Mac Pro, and
Yeah.
using the built-in FireWire and the FireWire from a PCIe card.
Hmm.
And I mean, I'm think how many cores were on the Mac Pro?
I think that is a dual core. Yeah. Oh no, it's a quad core. It was a quad core. Yeah.
So quad core Mac Pro. So what's kind of interesting is that current computers, current laptops are basically better than that Mac Pro.
I know, I know. That's also what we made a test run. I made it here on my i5 and MacBook, and see how it works. It was a bit flaky with just one FireWire port, but interestingly, it worked.
Right.
And I want to see how high the CPU and the rack load is, and it was pretty low. It was nearly nothing.
Right.
And I also made a picture of that and I put it on our Facebook site because I saw this on this quad core, this old Mac Pro. You see, there was a record load of something like 8% or something.
Wow, that's great.
With it, yeah.
So
nothing.
So the interesting thing to me is that, you know, you had the Mac Pro available to you, and that's great, but it's a big machine to carry out. I mean, for a 3-day festival, for that scale of a system, it's not that big a deal. But if you're just doing like you know, even if you were doing that many channels in a club gig or something like that, that would be a big machine to heft around. What's interesting to me is that, you know, if you look at, say, a current Mac Mini or a current MacBook Pro, the Mac Mini and the MacBook Pro both have FireWire on them, and the MacBook Pro Retina doesn't, but it also has 2 Thunderbolt ports, and then the other machines both have Thunderbolt ports as well. And so the thing is that basically the PCIe card is the same thing as a Thunderbolt PCIe adapter. I'm sorry, Thunderbolt FireWire adapter.
Yeah, right.
Except that, you know, there's a couple of benefits actually to the Thunderbolt adapter that Apple's put out, right? One is that as far as the hardware configuration goes, it is the same thing as built-in FireWire on all modern Macs. They use the same chipset, same driver, and it's the same PCIe path.
Wow. Okay. And isn't it that far that you have multiple FireWire buses on this Thunderbolt port?
So the thing is that basically for the Mac Mini and the iMac and for the MacBook Pros, those all have FireWire 800 on the motherboard, and then they also have one Thunderbolt port.
Ah, okay.
So the thing is that you can use the Thunderbolt port to add another FireWire bus, and you can have the same configuration as you had, except for on a portable machine.
Wow.
Now, if you have a MacBook Retina, they've taken away the FireWire port on the motherboard, but instead they give you 2 Thunderbolt ports.
Okay. And they're including also FireWire.
So the thing is that you can use both of those Thunderbolt ports for FireWire.
Yeah, right. And then we can do the same thing there with the MacBook. Wow. Yeah, this is nice.
Right?
This is nice. Yeah.
So and the thing is that the Thunderbolt adapter is, you know, very inexpensive. I think it's $29. And readily available. You can get it from the Apple Store or online. And it gives you a native FireWire implementation that allows the customers to take advantage of multiple boxes and multiple buses with no downside.
Yeah, right. Absolutely. Yeah, great. That's interesting. The thing is, Modo mentioned also that he said next year we're going to do this with 96K.
Okay.
And that would be perfect setup. Having a MacBook Pro and these 2 Thunderbolt adapters, 48 channels on the other side. Wow.
Right. Or perhaps, you know, by that time, the new Mac Pro, which has 6 Thunderbolt ports. Right. So you could do up to 6 buses, even if you were just, you know, even if you're still limited to doing FireWire based recording. And, you know, that machine's not big anymore. I mean, it's a very small, compact machine. So the fact that they've lost the PCIe card slots for a mobile I/O user is essentially a non-issue.
Right.
In fact, it adds more options for a lower cost.
You saw this box on the developer conference, don't you?
I'm sorry,
New
which
Mac
part?
Pro? You saw the Mac Pro on the developer conference?
Yeah, I did. I did. Yeah.
Okay.
It's
how big is that box?
It's about this wide.
Okay.
And maybe it's a little bit taller. I got to back up.
Okay.
It's probably around that tall or so.
Okay. All right.
So, you know, and like that big around.
Yeah.
So it's probably about 2/3 the height of the existing Mac Pro.
Okay.
And
yeah.
about 2/3 the diameter of it is about 2/3 the width of the existing Mac Pro.
Okay.
But it's about maybe 1/3 or 1/4 the depth of the existing Mac Pro.
Ah, interesting.
So
yeah.
you could probably put like 4 or 5 of the new Mac Pros in the same space as the old Mac Pro.
Ah, okay. Wow. Okay, that's pretty small. Yeah, I'm curious when this box is coming out, because we see Sean what it's gonna do for when they're gonna release that thing, and it's a pretty new concept when you think about no connection, no PCI card in there. I got a bunch of discussion about that with a couple of customers, and yeah, they're going forth and back. In my opinion, this box is a pretty nice concept. When you imagine you have this box, carry it with you, connect it to somewhere else, you just need those connectors, and everything is connected. And when you compare this to the box where you have everything inside, I like that.
Yeah,
I think it depends a bit on the price, what they're gonna charge for a box like that.
Well, I mean, they have to scale it with things like the Mac Mini. I mean, it's hard to tell. They haven't announced anything about pricing, and they're clearly targeting the professional user. So when you're looking at a professional user, you're also looking at people who are making money with the product, and the assumption is that they're going to be willing to pay for the advancements that they get. And we'll just have to see if that's commensurate with what the professional audio user wants to do. Certainly, it seems to me that if you're tied to PCIe cards, there's some drawbacks to this product, right? But just like with the Thunderbolt adapter for FireWire, they really haven't left the customer out in the cold, because what they've done is they've made it so that the PCIe is now exported out of the box through the Thunderbolt connectors. So you could get a PCIe to Thunderbolt chassis and use your existing PCIe cards, or you can use other non-PCIe or Thunderbolt-based peripherals. The only thing is that, there's added expense associated with that, and there's the fact that instead of having one unit that kind of has everything inside of it, you got to connect it all together. So it's going to be interesting to see how that winds up working out for the audio professional. But certainly the demonstrations that they talked about during the keynote, it's an impressive machine.
Yeah. Also from the CPU power, or from the computer power inside?
Yeah, it's all of that. I mean, it's a very powerful chip with very powerful GPU.
Okay.
And in fact, I believe that I don't remember exactly what they said about it, but I believe that there's GPU power that potentially is interesting to audio people.
Okay.
It's hard to say. The sort of the technical issue with the GPU stuff is that the GPUs are extremely powerful, and they're useful for a certain subset of audio applications.
Okay.
The problem is that the way that the system software for the GPUs is set up, everything's sort of like a batch operation. The software kind of schedules a batch on an operating system queue, and the operating system schedules the job onto the GPU and gives you the result when it's done. And there are no guarantees about latency in those queues. So, the thing is that even if the GPU could do your work in a small enough fraction of a second that you could use it to process audio in real time, there's no guarantee that your job will even get to the GPU by the time your deadline comes, let alone actually complete the job by the time your deadline comes. And so the thing is that there's even, for example, if the GPU was not being used by anything else, the likelihood is very high that everything would be fine.
Yeah.
But
Okay.
the problem from an audio user's perspective is that the GPU is a shared resource that's managed by the OS. The OS provides no mechanism for locking the GPU to a particular application, and it provides no mechanism for
Okay.
providing quality of service or deadline requirements. So the thing is that you can't say, well, I have an audio application that runs on the GPU, and I have this very short deadline, and as long as the GPU is not being used by anything else, then everything's fine. The problem comes that there are lots of things in the system that might use the GPU. So, like,
This is interesting. Hmm.
right. So, for example, we could be using the GPU for audio processing, and the user decides to open FaceTime, or even
Yeah.
worse, someone calls them on FaceTime, and FaceTime opens up, and maybe that schedules some jobs on the GPU, and there's no way to lock that out, and the job on the GPU for the video processing might take sufficiently long that the audio processing fails.
Okay.
So
Okay.
even though it's an incredibly powerful resource, it's not one that's really well suited today for real-time audio processing.
Yeah.
But potentially as they add more GPUs to the system and they recognize potentially additional places where these facilities could be used, it may be something that audio developers can take advantage of moving forward. They're just not quite there yet.
Okay. Okay. Is this? I had some discussion with a couple of users about that thing. That it seems like sometimes those DAWs seems to have problem with latency compensation when you're running huge, big sessions, taking a lot of CPU of it. It can't be that sometimes the latency moves a bit in the different channels depending on what happens on the channel.
Well, in principle, it shouldn't.
Yeah.
But there's a lot of complexity under the hood with latency compensation.
Yeah.
And in particular, latency compensation and processor management. Right. The thing is that when everything's running in one process thread on the computer, it's much easier to manage your latencies and ensure that everything completes in the order that it's supposed to complete in, and everything's ready when it's supposed to be ready.
Okay. Mm.
The only problem is that, about 6 or 8 or 10 years ago, Intel and PowerPC, as far as Macs are concerned, PowerPC before that, but Intel in particular, they all kind of came to the conclusion that they weren't going to be able to keep increasing the clock speed of the processors.
Mm-hmm.
Right? They kind of hit a wall in terms of clock speed. So that meant that each processor core was not able to get faster anymore. What they needed to do in order to make the systems faster was add more processor cores.
Okay.
Right? So when you add a processor core, you add, like, if you have a single core processor and you make it a dual core processor, you add double the compute power.
Mm-hmm. Mm-hmm.
However, the thing is that, most problems aren't easy to break up into two kind of independent processing streams. So the thing is that they benefit like general purpose computers, right? Because, if you're checking your email and you're copying a file and you have, say, a mixdown running and you're doing Skype, all of those things are kind of completely independent of each other, and each one could be running on its own processor core. And so if it was sharing the processor core, it would be 5 times slower. But because you have 5 processor cores that you can assign each one to a different task, figuratively assign each one to a different task, they can all pretty much run at full speed.
Okay.
So for general computing usage, you get a real big speed up from the multi-core processor simply because you have more than one thing going on in the computer at once.
Yeah.
When you're talking about doing things like audio processing actually has the benefit of being what's called a parallel. It's not embarrassingly parallel. Graphics is generally embarrassingly parallel. And by embarrassingly parallel, that means that basically, essentially, each piece of data can be acted on independently of every other piece of data. right? So that would be when you're doing like graphics work, various filters and processes that are done for graphics, literally the same algorithm can be run on each pixel independent of all the other pixels. That's embarrassingly parallel. In audio, you can't run the same algorithm on each sample independently of all the other samples because there's a time stream associated with it, right?
Yeah.
So the thing is that the next sample that you're going to output is in some way dependent on the samples that came before it. So you can't take a chunk of samples and treat them sort of independently of each other. You have to look at the history, and the history may depend on the output of the algorithm as well. So things like compressors and EQs, all of those things care about what happened in the past, both on the input and on the output. Okay? So the thing is that they're generally not embarrassingly parallel because you can't break it up that much. But they do tend to be very parallel in the sense that, at least for professional audio, we tend to work with multiple channels. And each channel can generally be treated independently or semi-independently. So when you have like a 32 channel mixer and you have 32 channel strips, one on each channel, running each computation of the channel strip algorithm for a particular channel in a parallel way is very difficult and maybe impossible to do. It depends on exactly how you think about breaking up the problem. But running each of the channel strips on its own processor core is very easy to do.
Okay.
Right? So the thing is that if you have like a 32 channel mix with 32 channel strips and you had a 32 core processor, you could in principle assign each of the channel strips to a different core and let them run in parallel, and then when they were all done, you could take their results and feed them into the mixer, for example. Right? So the problem is that you generally don't have as many processors as you have processes, right? So the thing is that you have to distribute the work across the processor cores. And then the other problem is that some of your channels are going to complete very quickly, depending on what plugins you have on them. And other channels, where you maybe have a lot of plugins, will complete more slowly. And you can't start doing the mixing until all of them are done, right?
Right. Okay.
So there's this whole synchronization aspect of synchronizing the work that's being done by the different cores. And the synchronization is associated with managing the latency between the channels, right? And the reason that you care about this is that, you have this great, say, 4-core or 8-core or 12-core computer that you want to run on, and if you don't spread the processing across all of the cores, then what winds up happening is that you get 1/4 or 1/8 or 1/12 the compute power because all the work's being done by one core. And people go and look in Activity Monitor and say, I'm getting glitches, but it's not using the entire computer. The flip side is that you would go and say, I want to go and run all of the cores. I want to spread the work across all the cores. But then you have the complication of synchronizing that work. And the synchronization will either introduce latency or will introduce some variability that could lead to glitching if things aren't managed properly. So it's a very complicated problem in order to get all of the use, the complete benefit of the processor out of the system. And that's even more complicated by actually doing the latency latency compensation. And it's even more complicated by doing latency compensation with buses. Because the thing is that the buses are crossing latency domains. So exactly where to compensate them, and you want to try to parallelize the buses running. It just makes it complicated. And, I can see that when you're trying to do this sort of multi-threaded processing where, occasionally things can slip and you do the computation the wrong way, and then you get the wrong latency compensation, and then all of a sudden the latency compensation is off.
Yeah, interesting. Because this is something that I watched so many times, especially with our well-known logic. Sometimes the buses are compensated and sometimes not. And you bounce a bunch of tracks into a stereo file, shut down the computer, start it again, do the bounce again, and then compare those two bounces. They're definitely different. And this is something what I could observe. And each door behaves a bit different. This is very interesting. That seems to me that a DSP system or DSP-based audio system is running much more stable this way, isn't it?
Well, one of the ways that you control that process is to introduce latency.
Okay, so you have a fixed latency.
Right. So the thing is that, you introduce a latency of routing from process to process.
Yeah.
Right. And that introduction of fixed latency, what that means is that, envision it this way. Let's say that you have 12 channel strips, and you have 12 processor cores, and you run each channel strip on each processor core, right?
Okay.
And after they're done running, you get a result. When you've gotten a result, you need to take the results from each of the processor cores and sum them together to get a final mix. If you say that I'm going to take the current samples and run them through the channel strips, and then put them into a buffer, and then when the next bunch of samples comes in, I'm going to take those and process them with the channel strips. And the stuff that I processed the last time with the channel strips, now I'm going to mix it. Right? That sets a fixed latency. You're buffering for one set of processes, and then the processes that then require all that stuff to be combined are working on the one from one iteration in the past. Then you don't have to wait, right? You can actually start mixing last iteration's block of processes right when you start processing. So you can put the mixer on yet another process core and let it run at full speed without having to wait for anything. But you've introduced one block of latency.
Okay.
So now the block of latency that you've introduced is going to be the size of the audio processing block, which is generally going to be the size of the audio hardware I/O buffer, right? So if the user sets it to 32, that would introduce one 32 sample block of latency. If it's set to 256, it would introduce an additional 256 samples of latency. And the thing is that on native systems, the block sizes are generally relatively large, right?
Yeah, okay.
So introducing that latency is a non-trivial introduction of latency into the system, right? On DSP systems, the block sizes are generally very small, usually one sample, maybe a couple of samples, right? So the thing is that if you introduce one sample of latency between sort of logical blocks, you don't really notice it. And that's sort of the system that, for example, TDM takes. Pro Tools TDM is they actually take it to a further extent. They don't actually schedule the processes within a specific strip. Every insert, every routing point from process to process introduces a block of latency.
Okay. But it was clearly defined how much it is. And
it's always the same amount of latency by introducing another plugin. Now, the interesting thing about Mio Console is that we don't do that. We schedule the execution of the process blocks in the order that they need, so that when one's done, the next one has the data that came out of it, and we can run them all in one CPU or one sample cycle.
So the all over latency in the 2D DSP processing is just one sample in and one sample out?
Yeah, and I think it works out to be essentially one sample for processing. So it's like three. It's like three samples.
3 samples.
Right.
It doesn't matter what you do, and you can until the CPU is telling you, or the DSP is telling you, now that's a bit too much. But as long as it's still 3 samples.
Correct.
Very nice. Yeah. Okay. It's put a little bit light on that thing, because from time to time I hear this from customers saying, when I'm running things through the Mio mixer, it sounds better like in my DAW. This is saying that we hear a bunch of times. No one really can't explain this. Maybe it's a little bit goes in this direction, that you still have to figure out what the DAW is doing on a CPU on your computer in comparison to a system that is dedicated to do that work and nothing more.
There is always a possibility. I mean,
Yeah.
as we said the last time we talked about this, it's not clear to me why a properly implemented system, two properly implemented systems with the same settings wouldn't sound exactly the same. But we certainly do hear that a lot from people.
Yeah,
so
definitely.
I don't know exactly what to extract from it, but we're reasonably sure that the stuff that we're doing is properly implemented.
Yeah, this is the difference. Yeah, you get a chance to do this. If you imagine some of the DAWs are pretty old and they have some code running there that's also very, very old, and maybe this do some trouble. Well, however.
Yeah, exactly.
It is okay. I'd like to come back to one thing that I found very interesting in Haldan, because when you're doing the tracking in the record panel, you have those recording log where you can see how it is done and how it works. And well, I go after each band has played, I just take a small look at it, how it was done, and it was really 570 gigs, and we have no fault message, no glitch occurred or something like that. And what I'm asking myself was, how is this tracking done? When you're doing this, there's all this data that comes in and is written on a disk. Somewhere it is observed and said, okay, that was not.
Okay, yeah. That's reasonably easy to explain. So,
yeah, there is some more behind, because I asking myself, how is this FireWire connection working? Because I plug it in and it works, but I do not know how. And maybe this is something could be also interesting for another users.
Yeah, I think that maybe what we'll do is we'll break that out into a separate tech talk, because I think that it's going to require a little bit of drawing and pointing at things and explaining how it all works. And actually, it's kind of interesting the way that the FireWire transport through with core audio to the boxes works is in some ways very similar to the way that the record panel works. They're based on similar mechanisms. I mean, the scales are different, and the requirements are a little bit different, and how it all winds up working in the end is a little bit different. But the overall concept is pretty similar. So let me just briefly explain the overall concept of how the record panel works, and then maybe we can, in a future tech talk when we're talking about the details of the core audio transport, we can go into that a little bit more detail, and we can refer back.
Very good idea.
So basically, the way that the record panel works is we connect to the core audio driver. We believe in eating our own dog food. So rather than trying to communicate directly with the box and bypassing core audio, the record panel uses our core audio driver to talk to the box. And
so is this the reason why we do not need the aggregated device for the record panel?
Right, because we understand about the structure of our devices, and we can identify them all and aggregate them within the record panel. But but we are using the core audio driver, and there's a couple of reasons for that. One of which is that we want to make sure that the application that we have that stresses the system the most is using all of the components of the system. And that means that when someone uses it with a different app, they're going to get the same results rather than us being like, oh, well, it works great when we use our super secret connection to the device, but when you try to use Logic, well, all bets are off.
Yeah. Okay.
The other aspect of us using the core audio driver means that when we're using the core audio driver and Logic is using the core audio driver, or iTunes is using the core audio driver, it means that you can use the record panel at the same time with any core audio app or multiple core audio apps, as opposed to other systems like I'm pretty sure that this is the case for like Pro Tools HD, maybe Pro Tools Native. They use a direct connection to their software. They don't use the core audio driver. So when Pro Tools is talking to their hardware, no other audio app can talk to their hardware.
Right? Yeah, right. Okay.
So we want to make it so that you can sort of utilize both simultaneously.